This is K Devender Reddy, Assistant Professor, Institute of Aeronautical Engineering College, AAA Department. Today we are going to discuss the working principle of three-phase slip-ring induction motor. The working principle of three-phase slip-ring induction motor is similar to the working principle of three-phase squirrel cage induction motor, but there is a difference between these two types of the rotor series, the rotor winding. In case of the wound rotor or the slip-ring induction motor rotor, the rotor have a three-phase star or delta connected winding, preferably a star connected winding, and the three phases are connected to the slip rings through brush arrangement. There will be a possibility to connect the external load to the rotor winding or external resistive band to the rotor winding to increase the resistance of the rotor, to increase the starting torque of three-phase induction motor, and also to decrease the starting current of three-phase induction motor. There is a possibility to change the starting current as well as the starting torque in case of the slip-ring induction motor. That is why I am more focused on first of all the working principle of slip-ring induction motor. Then after later we focus on the working principle of three-phase squirrel cage induction motor. The working principle not much differ between these two types of the rotor, but the difference is the rotor winding in case of the three-phase squirrel cage and the three-phase slip-ring induction motors are different. In case of the three-phase squirrel cage induction motor, the rotor have copper or aluminum bars which are permanently connected to the end rings to make the short circuit or to make the closed circuit in the rotor circuit, and there is no possibility to increase the resistance of the rotor circuit in the case of the three-phase squirrel cage induction motor rotors. But in the case of the slip-ring induction motor, we have star connected three phases winding which are 120 degrees apart spatially, and these three windings are connected to the three slip rings, and the three slip rings are connected to through the brush arrangement to the external load or external resistive bands. Here I am showing three-phase slip-ring induction motor cross-sectional view, and this green mark circles represents the stator winding, and this red marks represents the rotor windings and the rotor drum as well as the shaft. Cut sectional view. The rotor slots here we shown. Inner circles represents the rotor slots, and the outer circle represents the frame, and the second circle represents the stator slots, and the green color represents the stator winding, and this red color represents the rotor winding. Rotor winding of three-phase induction motor. So here we will analyze the working principle in a case to case. So before going to analyze the slip-ring induction motor working principle in a case wise, first of all we have to discuss about the Faraday's laws of electromagnetic induction and the basic principle of three-phase induction motor. So as like all the rotating machines, the induction motor is also have a working principle based on the Faraday's laws of electromagnetic induction. So we know the Faraday's laws, the rate of change of flux cutting according to the Faraday's laws. Law 1 and law 2 represents the rate of change of flux cut by the conductor is proportional to the induced EMF, and the magnitude of induced EMF equal to minus n times of rate of change of flux cutting. So similarly in the case of the three-phase induction motor, the stator is excited by a three-phase balanced supply, whether it is a star connected or delta connected, which is connected to the three-phase AC supply, preferably a 50 Hz frequency. And when the three-phase windings are excited by a three-phase balanced supply, it produces a rotating magnetic field. We can also call the stator rotating magnetic field. Why I am specifically mentioned the stator rotating magnetic field? In the next part, we are also discuss about the rotor magnetic field also. It is also rotating in nature. That is why I am specifically naming the magnetic field produced by the stator is stator rotating magnetic field, SRMF. Stator rotating magnetic field, SRMF, and the rotor rotating magnetic field with the naming as RRMF. Rotor rotating magnetic field. So it produces the stator rotating magnetic field, which rotates the speed or which revolves the speed of synchronous speed ns. So when a three-phase star or delta connected winding is excited by a three-phase supply, which produce a stator rotating magnetic field, which is of rotating with the speed of synchronous speed called ns. Once it produces a rotating magnetic field, in the case 1, the stator is open circuited. I'm assuming is the case, the first one is the stator is, the rotor is at standstill condition. The rotor winding is open circuited and the rotor is at standstill condition. I am assuming the case 1 when the rotor winding is assumed to be open circuited. Assume the stator winding and rotor winding both are star connected, and now the stator is connected with a three-phase balanced AC supply which produce the stator rotating magnetic field, and it is revolving with the speed of synchronous speed ns. In this situation, when the rotor is open circuited, the stator rotating magnetic field is rotating with the speed of ns with respect to the rotor structure, which is at standstill condition. So the flux cutting by the rotating magnetic field links the stator conductors, the stationary stator conductors. So the magnetic field is keep on revolving or rotating with respect to the synchronous speed, and the stator conductors are stationary. There will be a large relative speed between the stator magnetic field as well as the stator windings. So there will be an induced EMF in the stator conductors. There will be an induced EMF in the stator conductors according to the Faraday's laws of electromagnetic induction. There will be an induced EMF in the stator conductors I am naming as E1 per phase. Induced EMF in the stator winding per phase equal to 4.44 times of F1 is the frequency of the supply and N1 into KW1. N1 is the stator turns per phase and KW1 is the winding factor. KW1 is the winding factor. Winding factor of the stator. Here, there will be an induced EMF in the stator conductors, which is of E1 per phase equal to 4.44 times of F1 into N1 into KW1. So here, the frequency of induced EMF in the stator, I am represented with the F1 here. The frequency of the stator induced EMF is F1, which is equal to the relative speed between rotating magnetic field and the stator structure or stator winding into number of poles by 120. Fs, generally the frequency equal to speed into number of poles by 120. Here the speed is the relative speed between the stator structure or stator winding and rotating magnetic field. That is relative speed, that is equal to, here the relative speed is ns because the stator winding is stationary. The relative speed is ns minus 0. So the ns is the speed of the rotating magnetic field and the speed of the stator windings are 0. So it is stationary. So I am representing the relative speed equal to ns into number of poles by 120 equal to f. So f equal to nsp by 120, that is equal to supply frequency. So I am making the equation which is equal to E1 per phase equal to 4.44 times of F1. So F1 becomes now F into N1 into KW1, that is a winding factor of stator. So now I am making the induced EMF per phase equal to 4.44 times of F into N1 into KW1 at the starting, that is when stationary condition and the rotor is kept open circuited. So frequency of your stator induced EMF equal to frequency of your supply, that is F1 equal to F at the time of the rotor is assumed to be open circuited and both should be star connected. In the next case, the induced EMF in the rotor, that is when I am assuming the case next one is the rotor is closed circuit or short circuited through the slip rings and pressure arrangement. By any of the external means I am short circuited the rotor winding. So when the rotor winding is short circuited, so according to the Faraday's laws, whatever the induced EMF in the stator winding because of the Faraday's laws, but similarly the induced EMF also induced in the rotor circuit, that is equal to E2 naught, that is induced EMF in the rotor at starting, that is at standstill. Induced EMF in the rotor at standstill, that is E naught, E2 naught equal to 4.44 times of F2, Phi1, N2 and Kw2. So this is the induced EMF in the rotor circuit according to the Faraday's laws, because the stator magnetic field is revolving with respect to the synchronous speed, and with respect to the rotor at standstill condition, the relative speed becomes ns only. At starting means, at standstill means the rotor speed is zero. That is, I am assuming the rotor speed nr. That is, at standstill it is zero. When rotor speed is zero, magnetic field is rotating. The stator rotating magnetic field is rotating with respect to the rotor is ns. That is the synchronous speed. Let us, I am assuming it is a 1500 rpm for a 4-pole machine. For example, it is a 1500 rpm. So it is rotating with a 1500 rpm, and there will be an air gap between the stator and rotor due to the induction. Due to the induction principle, the whatever the magnetic field which is available in the air gap also links the rotor conductors, and the rotor conductors are steady constant, that is at standstill position. So the maximum rate of flux cutting will be possible. So due to that maximum rate of flux cutting by the rotor conductors, it is already short circuited or it is closed circuited, and induced EMF in the rotor circuit is E2 not equal to 4.44 times of F2, Phi1, N2 and Kw2, where N2 is the rotor turns per phase and Kw2 is the winding factor of the rotor, and F2 is obviously frequency of induced EMF in the rotor. So now let us write down the expression for frequency of the rotor induced EMF. F2 equal to relative speed, as similarly we know relative speed into number of poles by 120. So we know already the rotor at standstill condition. So that is ns minus speed of the rotor, that is ns minus, that is the relative speed is ns minus nr, where nr is at standstill, it becomes 0, ns minus 0, ns minus 0, that is ns only. So that is why I am writing here ns into P by 120, which is equal to frequency of supply. So at standstill condition, the induced EMF in the rotor circuit frequency, that is F2 equal to frequency of your supply only, that is frequency of your stator supply. So rewrite the expression E2 naught per phase induced EMF in the rotor circuit per phase at standstill condition, it is equal to 4.44 times of F into Phi1 into N2 into Kw2. That is, F is the frequency of the rotor induced EMF, which is equal to the supply frequency at standstill condition. So the next one. So from this discussion, we also write the expression for induced currents in the rotor circuit. So in the previous case, we assumed the first is rotor is open circuited. At that condition, the induced EMF in the stator, we write the expression for induced EMF in the stator, and we already write the expression for induced EMF in the rotor circuit. In the next case, when rotor is short circuited or closed circuited, then after, when rotor is rotating, how the rotor is rotating, how the torque will develop, how the force will develop in the rotor, that we need to discuss. Then after, we need to write down the expression for induced currents or current circulated in the rotor I2 per phase. Now, when the rotor circuit is short circuited, the induced EMF in the rotor circuit is, so induced EMF is E2. Already we know the impedance of the rotor is, I am assuming, as a Z2, right? I2 per phase, induced current, the rotor circuit short circuited current I2 per phase equal to simply E by Z, that is E2 by Z2. The interaction of the rotor current with rotating magnetic field experiences a force and produces a torque in the rotor of a three-phase induction motor according to the Lorentz force equation. What happens when the rotor is closed circuited? When the rotor is closed circuited, a current is circulated in the rotor winding, that is called rotor induced current I2 per phase, which is equal to V by Z, that is induced EMF in the rotor I am naming as E2, and the impedance of the rotor is Z2. So this rotor current in a closed circuit produces also a rotating magnetic field. So there are two magnetic fields. One is a rotating magnetic field of the stator, and another magnetic field, the rotor rotating magnetic field. The interaction of this rotor current or rotor magnetic field or rotor flux with the stator flux in the air gap will produce as a force, That force in the rotor is, it produces a force or torque in the rotor circuit to turn it into a particular direction. So direction of the rotation of the rotor is very similar direction of the rotating magnetic field. Very similar direction of the rotating magnetic field. Why it is according to the Lenz law, why it is rotating? I am explaining now. According to the why the rotor is rotating with the same direction of rotating magnetic field, it is because of according to the Lenz law. So what states the Lenz law? Effect always opposes the cause of its production. Here the effect is a torque, and its cause is how the torque is developed because of the rotor current. So rotor current is circulating in the rotor winding because of the induced EMF in the rotor circuit. The induced EMF in the rotor circuit is because of the flux cutting. So here the cause is flux cutting, and the result is your torque. So according to the Lenz law, the effect is nothing but, or result is nothing but torque, and its cause is flux cutting. So your torque should opposes your flux cutting in the rotor, air gap to the rotor. So that is why the rotor is try to rotate in the same direction. It is rotating in the same direction in the rotating magnetic field of the stator, to minimize the flux cutting of rotor conductors. Because at standstill or at starting, the relative speed, what is the relative speed? A relative speed equal to, at starting, relative speed equal to generally ns minus nr. At standstill, nr becomes 0. So the relative speed equal to ns only, that is the speed of the rotating magnetic field is synchronous and the speed of the conductors of rotor is 0. So the maximum rate of change of flux cutting will come into the picture. When the rotor starts rotating, the relative speed is ns minus nr. There is a definite speed of the rotor as well as the definite speed of the stator magnetic field. So here the rotor is rotating in a direction of the magnetic field, that is a rotating magnetic field. It try to reduce as the relative speed. At starting, the relative speed is maximum. Once the rotor starts rotating, the relative speed is decreases. So once the relative speed is decreases means your effect of rate of change of flux cutting also decreases, because both are rotating. At the time of the starting, one is stationary, that is rotor conductors are stationary. Stator magnetic field is rotating with a synchronous, that is ns. So that is why the maximum induced EMF will come into the picture in the rotor circuit. But whereas in the case of running condition, a rotor starts rotating, so the rate of change of flux cutting will be decreases. The rate of change of flux cutting is purely depending upon the relative speed of the three-phase induction motor, that is ns minus nr. Anyway, the ns synchronous speed is constant, so it is depending upon the speed of the rotor circuit. So it is anyway depending upon the speed of the rotor circuit. So in this case, the torque will produces in the rotor circuit. It tends to rotate the rotor in the same direction as the rotating magnetic field to minimize the flux cutting effect in the air gap. So it try to decrease as the induced EMF in the rotor conductors, and the rotor try to reach or try to catch the speed of the rotating magnetic field. So, but it is never attains the speed of the rotating magnetic field, which falls back by a speed called a slip speed. Slip speed equal to ns minus nr. Slip speed equal to ns minus nr. The rotor try to rotate and try to catch the speed of the magnetic field, but it never catches the speed of the rotating magnetic field. It falls back by a factor called slip. So slip equal to ns minus nr, the relative speed of the stator magnetic field and rotor speed by ns. In terms of the percentage, you will get into 100. The percentage slip equal to ns minus nr by ns. And frequency of the induced frequency of rotor, also we can slip equal to ns minus nr by ns. From this, you can also derive the expression for rotor speed nr equal to 1 minus slip times of the speed of the stator magnetic field ns. The rotor speed equal to 1 minus s times of the rotor, 1 minus s times of the stator rotating magnetic field ns. So you can also derive the expression for a rotor frequency f2 equal to, generally the rotor frequency equal to relative speed ns minus nr, rotating relative speed into number of poles p by 120. So that is 120. So from this you can derive the expression for ns minus nr by ns into pns. So here these will cancel and it gives you rotor frequency f2 equal to s times of the frequency of the stator. So rotor frequency f2 equal to, from the expression, slip times of the frequency of stator, that is the frequency of the supply. In this case, we derive the expression for rotor frequency, which is equal to slip times of the frequency of the stator or a supply, and slip speed equal to ns minus nr, and the percentage slip equal to ns minus nr by ns into 100. And the next I am assuming the another case, if the speed of the rotor is reaches or it is equal to the speed of the rotating magnetic field, then what happens? The speed of the rotor physical rotation or the speed of the rotor conductors are equal to the speed of the magnetic field. Then what happens? In that particular case, when the speed of the rotor attains the or reaches the speed of the stator magnetic field, so what happens? Relative speed equal to ns minus nr. When this nr reaches the ns, so relative speed equal to ns minus ns, that represents 0. Relative speed equal to 0. Relative speed equal to 0. Relative speed between the stator rotating magnetic field and rotor conductors are 0. There will be no flux cutting action. There will be no flux cutting action, so no induced EMF. No EMF will be induced in the rotor conductors. If there is no induced EMF in the rotor conductors, so no rotor current. No induced EMF, there will be no rotor current. No forces will be developed, there will be no forces. The forces are 0, then torque will be 0. Force is 0, that means torque is 0. That means rotor will not start. Rotor will comes to standstill position. rotor will comes to standstill position. When the rotor reaches the speed of the magnetic field, synchronous speed, there will be a no flux cutting action. If there is no flux cutting action, induced EMF in the rotor circuit is zero. So the no induced EMF and no induced currents in the rotor circuit. If there is no rotor current, no forces will develop in the rotor circuit. There will be no torque in the rotor. And once it reaches the speed of the synchronous, the rotor induced current or rotor currents are zero. So the forces will not develop and the rotor slows down and reaches to the standstill condition. The rotor will slows down because of the frictional forces in the rotor rotating bodies, and it reaches to the standstill condition. So this is a session. In the session, we discussed the case-to-case study of working principle of three-phase slip-ring induction motor and derivation for rotor frequency and slip as well as the relative speed. Thank you.
Like, share and subscribe. Hit the bell icon for more updates. Like, share and subscribe. Hit the bell icon for more updates.